Let us get started with a big picture overview. Week 3, Data Cleaning, Handling Missing Values, Noise, and Outliers. Welcome! This week we learn about making our data trustworthy. Dirty data can lead to bad predictions. Today we practice cleaning real-world datasets and prepare them for data mining. Running the cell now. Think of parts of your day where missing or noisy data might cause mix-ups. Ready to spot some problems in real data? We will silence warnings to keep our notebook clean and clear. We import Python's warnings module. Import NumPy as NP. We set the random seed to 42 for reproducibility. We turn off all warnings so the output is easier to read. Running the cell now. Here, we set a random seed and suppress warnings to create a clean, reproducible environment for data cleaning. This ensures that any randomness in handling missing values or outliers is consistent across runs, helping us focus on the cleaning steps themselves without distraction from warning messages. Notice how there is no more warning clutter in the notebook now. We will use the Titanic dataset for our data cleaning practice. Data setup, Titanic dataset. Let us use the Titanic dataset. It is famous and full of interesting details. We will work on cleaning this data step by step. Running the cell now. Have you heard of the Titanic story? The data is real and gives us lots to explore. Let us load the Titanic data and take a peek at its contents. This cell is called Data Setup. We import pandas. Pandas is a tool that helps us handle tables of data easily. We load the Titanic dataset from a public GitHub repository. We bring the data into a data frame named df. We print the dataset shape. This tells us how many rows and columns we have. We print the first 3 rows to preview the raw data. Running the cell now. The dataset contains 891 rows and 12 columns, indicating a sizable number of passengers with various details. The preview shows key columns like passenger ID, survived, P-class, name, sex, and age, which are crucial for understanding and eventually cleaning the data. This initial exploration helps us confirm the structure and guide our next cleaning steps. Glance at the output. Which columns look most important for survival prediction? Let us check our Titanic data for missing values, which are basically holes in the information. Step 1. Spotting missing values. Missing values are blanks or nars where information is lost. Finding them is the first step to cleaning data. Running the cell now. Imagine if your birthday or address was missing from your school record. That is how data feels with missing values. Now, let us actually see which columns are missing values and how much is missing. We check the total and percentage of missing values per column in the data frame. We count the number of missing, null, values in each column using isNull.sum. We calculate the percentage of missing values by dividing counts by total rows and multiplying by 100. We create a new data frame showing both the missing counts and their percentages rounded to 2 decimals. We print only the columns from the summary data frame that have 1 or more missing values. Running the cell now. This output highlights columns in the dataset with missing values, showing both the count and percentage missing. Notice that the cabin column has a very high missing rate, 77%, which indicates a significant amount of data loss, while age and embarked have smaller but still important gaps. This helps us identify where to focus cleaning efforts in our data pre-processing step. Try this: which columns should we pay attention to before analysis? Visuals can help us spot pattern and scale of missing data better than tables. We add a comment explaining that we'll visualize missing data with a heat map. We import the Seaborn library, which simplifies creating statistical graphics. We import Matplotlib's PyPlot module to control the plot display and size. We define the size of the figure to make the plot easier to see. We draw a heat map highlighting missing values. Missing data appear in yellow. We set a descriptive title so viewers understand the plot's purpose. We display the plot on the screen to visually inspect missing data. Running the cell now. This heat map highlights exactly where data is missing in the dataset, with bright spots indicating blank or NA values. Notice how the pattern of missingness varies across columns. This helps us identify which features need cleaning or imputation first. Spotting these gaps visually guides our data cleaning strategy in the initial step of handling missing values. Can you tell which columns or rows have the biggest missing patches? Let us explore methods for handling missing values so we do not lose useful info. Step 2. Handling missing data. Now let us fix missing values. Different columns might need different solutions. We will try several common strategies. Running the cell now. Have you ever had to guess a forgotten answer on a form? We will try similar strategies now. Age is often missing in real data. Let us fill blanks using the median instead of the average, because age data is often uneven. We find the median value of the age column, so we can use it as a substitute. We fill in all missing age values with the median. Median is the middle value and works well for uneven distributions. We print which value was used to fill empty age entries. Running the cell now. The output shows that missing values in the age column were replaced with the median age of 28.0, which is a robust choice for skewed data since it better represents the typical value than the mean. This step demonstrates how to handle missing data thoughtfully by using a statistic that minimizes distortion in our dataset. Why do you think median is better than the average for this? For text columns like embarked, we often use the most common value, called the mode. We find the mode of the embarked column. This is the value that occurs most often. We fill the missing embarked values with this mode. We print which value is being used to fill the blanks. Running the cell now. Here, we've identified the most frequent port of embarkation, S, and filled the missing values in the embarked column with it. This step ensures no gaps remain in this key categorical feature, which helps maintain data consistency for further analysis. Notice how choosing the mode preserves the natural distribution of embarkation points in the dataset. Can you spot where the most common embarked value might affect later analysis? Sometimes, when a column is mostly empty, it is safer to drop it altogether. We remove the cabin column from our data frame. Cabin had too many missing values and could create problems if imputed. We print a message to confirm the column was dropped. Running the cell now. Here, we dropped the cabin column because it contained too many missing values, which can negatively impact our analysis. This step highlights a practical approach to handling missing data by removing columns that are largely incomplete, streamlining the dataset for more reliable results. Try this tip. If you had very little data in a column about movie reviews, would you keep or drop it? Now let us check for numbers that do not fit. These are called outliers. Step 3. Handling outliers. Outliers are unusual values that can skew our analyses. We will use charts and simple math to spot them. Running the cell now. Imagine you suddenly scored 9,000 points on a quiz. That would be an outlier. Box plots are a fast way to spot outliers using little boxes and whiskers. We create a box plot to visualize outliers for the age and fair columns. We set the figure size to make the plots clear and easy to see. We start the first subplot on the left for the age box plot. We draw the box plot for the age column to show its distribution and outliers. We add a title to identify the age box plot. We move to the second subplot on the right for the fair box plot. We draw the box plot for the fair column to show its distribution and outliers. We add a title to identify the fair box plot. We adjust the layout so that the subplots don't overlap and fit well. We display the plots on the screen. Running the cell now. This output displays two side-by-side box plots for the variables age and fare, highlighting their distributions and potential outliers. Notice how the whiskers and any points beyond them indicate unusually high or low values, which could skew analysis if not addressed. This visualization helps us identify which values might need closer examination or treatment in our outlier handling step. Look for dots or points outside the boxes. Those may be our outliers. Let us spot fare outliers using the IQR method, which is a safe rule based on quartiles. We find outliers in the fare column using the interquartile range IQR rule. Calculate the first quartile, Q1, the 25th percentile of fare. Calculate the third quartile, Q3, the 75th percentile of fare. Compute the interquartile range IQR as the difference between Q3 and Q1. Determine the lower bound for outliers as Q1 minus 1.5 times the IQR. Determine the upper bound for outliers as Q3 plus 1.5 times the IQR. Select rows where fare is less than the lower bound or greater than the upper bound. Print the number of outliers found in the fare column. Running the cell now. This output shows that there are 116 outliers in the fare column, identified using the interquartile range IQR method. Notice how the code calculates the lower and upper boundaries to flag fares that fall unusually low or high, which helps us isolate extreme values that could distort our analysis. This step is crucial for cleaning the data before drawing reliable conclusions. Practice time. What other features might have outliers worth checking? Sometimes values are noisy, like test scores that wiggle a tiny bit. We will use bins to group them. Step 4. Smoothing noise. Noise means random errors or small fluctuations. We can use rounding or binning to smooth it out. Running the cell now. If a column is very noisy, would grouping help simplify the pattern? Let us create age groups. This helps reveal patterns hidden by noisy details. We define bins for different age ranges, naming them child, teen, adult, or senior. We specify the boundaries for each age bin in a list called bins. We create a list of labels corresponding to each age bin. We assign each passenger into one of these groups using pdcut and add it as a new column age group in the data frame. We print the first 8 rows of age with their age group side by side to verify the result. Running the cell now. Here, we bin continuous age values into categorical age groups to reduce noise and simplify analysis. Notice how ages like 22 and 38 are grouped as the adult, while a very young age like 2 falls into the child. This step smooths out minor variations by creating broader categories that highlight meaningful trends over individual age fluctuations. How could grouped ages help you compare children and adults in the dataset? Now we take a look at our clean data to check the results. We add a comment to indicate that we will preview the clean data. We print the first 5 rows of the data frame to inspect the clean data sample. Running the cell now. This preview shows the first 5 rows of the clean Titanic dataset with passenger details like age and fare now processed and categorized into age group. Notice how age group replaces raw age values to smooth out noise by grouping ages into broader categories, which simplifies analysis by reducing random fluctuations in the data. This step is key for making patterns clearer and improving model stability in later analysis. Can you see the age group filled in and missing values handled? Here comes a quick challenge. We will fill a missing value using your own answer. Minute practice, fill a missing value by hand. Suppose we spot the very last missing value. Let us try filling it manually and see the effect. Running the cell now. Ready? Try the code cell below and make your pick. Let us manually patch a missing age. You can type any age value you like at the prompt. We find the index of the first missing age if there is still one left. Currently, we do not have any missing, so let us introduce a missing age. Now, we check if any missing age values are left. If so, we ask you to enter a value with input. You get to pick the replacement. Your answer updates the missing spot. We convert what you type into a floating point number. We print a confirmation to show the value has been added. If there were no missing ages, we print that the job is complete. Running the cell now. Here, we've manually replaced the missing age value at index 1 with 27, demonstrating how to fill individual missing entries by hand. Notice how the code identifies the exact missing spot and updates it, reinforcing the practice of targeted imputation before moving on to automated methods. This confirms that the dataset is now fully complete in that column, aligning with the lesson goal of handling missing values manually. Want a tip? Try entering unusual ages, like 0 or 110, and see what you think. Let us recap what you learned so far this week. Recap: you cleaned Titanic data. Great work today. You loaded a classic dataset, identified and fixed missing data, found outliers, and smoothed noisy details. With these skills you are ready for any beginner data mining project. Running the cell now. If you like this, try loading another dataset and see if you find similar problems. You are becoming a real data detective. Give these challenges a try to lock in your skills. Practice challenge and next steps. Try counting missing values in a different column. Make a plot that shows outliers for SIB-SP or PARCH. Look for a public dataset and check for missing values using methods today. Subscribe if you enjoyed this lesson. New data mining tips every week. Running the cell now. Let us practice and grow as data scientists. See you in the next video.